Hello my friends, this is Mr. Cozy and this is video 46, inverses. We will talk about the definition of an inverse, talk about why 1 to 1 matters, and talk about how to find inverses. So let's get started. Okay, suppose f of x is a 1-to-1 function. By the way, guys, this is the definition of an inverse. Okay. Then there exists a function, and it's actually a 1-to-1 function called f inverse of x, and that's f such that if x comma y is a pairing in f, then y comma x is a pairing in f inverse. So the inverse of a function takes every point in the function and it flips the x and y values. Okay? So if for an example, let's say f has 3, 2 as a pairing, then f inverse has 2, 3. It uses all of the y values of f as x values for f inverse. Okay, that's the definition of an inverse. So let's take a look at an example that's a table. Let's suppose that f consists of the following pairings of numbers: -2, -3, 0, 1, 4, and 5, 5, and 7. Okay, this is a 1-to-1 function. None of the x's repeat, none of the y's repeat. To create f inverse, all I need to do is to exchange the x. I wanted that to be blue. Exchange the x and y values. So all of these y values become x values, and the matching x values become matching y values. Okay, so that's how you construct an inverse from a function, is you exchange x and y. So in this example, we see that f of 5 equals 7. Therefore, f inverse of 7 of this y value, remember that this was a y value in f. If I use that y value as an x in f inverse, I get the matching x value as a y value. Okay, because inverses exchange x and y values. Okay, another way to think of this is that inverses undo each other. Okay, I put in a 5 into f and got a 7 out of it. If I put that 7 into f inverse, I end up with a 5 again. So no matter what I do, or no matter what I put into f, if I do f inverse of that result, if I compose f and f inverse, what I get back is whatever x I put in the first place. Inverses undo each other. Okay? Now, let's talk for a second about this requirement of one-to-oneness, that for there to be an inverse, the function has to be one-to-one. And let's look at a classic example of a function that is not one-to-one. Let's look at x squared. Okay, these are the anchor points for x squared. Now we can see that this is not one-to-one. If I try to take the inverse of x squared, remember that I'm exchanging x and y values. So what's going to be the problem with my inverse when all of these y values become x values? My problem is this is not a function. Okay, this is why for there to be an inverse, a function has to be one-to-one. It's got to be one-to-one. Now, the good news is if a function isn't one-to-one, there are games that we can play to make it one-to-one and maybe come up with something like an inverse. For instance, a common thing that we do in this case is we just say, you know what, let's ignore everything less than 0. And then what's left is one-to-one. Okay, now there's some consequences to that action that you have to reckon with later, but at least, and we'll talk more about that tomorrow, but at least what you get at the end is something that is one-to-one and has an inverse. By the way, guys, here's a question. If f is one-to-one, then it has an inverse, and that inverse is one-to-one. So if we look at, in this example, f inverse is a one-to-one function. So what's the inverse of f inverse? Think about it. Actually, you know what? Think about it. Write it down on a sheet of paper and hand it in tomorrow. Okay? What's the inverse of f inverse? And if you aren't sure, think about this example. Think about finding the inverse of this and what you end up with. Okay? All right. Let's look at one last thing and then I'll let you go. And for this, I'm going to have to change to a grid. So let's do that. Okay. I'm using a new program, seeing how it works out. So let's imagine a one-to-one function that's going to be a very simple function. It's going to look like this. Okay, this is f. This is a one-to-one function. I want to graph f inverse. That's what I want to do. I want f inverse. So my first step is looking at the graph. I need to come up with a list of anchor points that will let me recreate the graph, and I've kind of made them for you right here. So 1, 2, 3, 4, 5, -5, -4, -3, -1, 1, 1, and 2, 3. Okay, these are the anchor points for f. So if I want to make f inverse, I'm just going to exchange all of the x values and all of the y values of f. And this is f inverse. Now, very important, when I plot these points, I need to plot them in the same order that they appeared in for f. But if I do that, -4, 1, 2, 3, 4, 1, 2, 3, 4, 5, -4, -5, -1, -3, 1, 1, 3, 2. What I get is F inverse. Okay? And looking at these two graphs, we notice a cool thing. And this is a neat property of inverses. The graphs of any function f, and this is any function f, and its inverse, are symmetric about the line y equals x. So if I look at this line here, that's the graph of y equals x, we see that f and f inverse are symmetric around that line. And I think that's a pretty cool property. Okay? Okay, we're gonna wrap this up here because I've sent enough stuff your way. Have a great day, and I'll see you later. Bye.